little this little start button which blinks and blinks and blinks and blinks, and they told me it's not really started until the blinking stops. So there, the blinking stopped, and so I'm gonna get going. Um, Alex Bakes, I don't think they've hooked up, if I'm looking correctly. They look like I'm looking at them underwater or something. The school's all pixelated. So I am recording. Sackett's Harbor's on a 2-hour delay today, and so I'm not expecting to see them this morning. So material we talk about today, other than the fact I'm just going to talk very briefly about the end of the continuity part. Other than that, the material we talk about today is not on the exam on Wednesday. We're still having an exam on Wednesday and so on. I did post a collected assignment this morning for Wednesday. The neat part is it's a really, really excellent practice for the exam on Wednesday, so the two will actually tie in quite nicely. Might see stuff like those on the exam on Wednesday. Hint, hint. So make sure that you go and you take a look at that. Did open up a couple more sections of WebAssign due at the end of the day, on Friday. So we've got some other stuff that's been opened up there. Put some not collected work out there as well. So hope everybody had a good weekend. It's kind of a icky weather weekend. It's like the third year in a row that we've had Super Science Saturday here in the snow. And so it is what it is. And I love how they gave us this winter storm warning. And probably in Copenhagen, you've had a little more snow than we have maybe here in Watertown. But I was like, okay, 2 to 3 inches yesterday, 2 to 3 inches overnight, 2 to 3 inches today, or whatever they were talking about. I'm like, this is not a winter storm. Okay, this is winter in the North Country. Seemed kind of dumb, but I know it fit their definition. So I could tell that the meteorologists, especially the ones in Syracuse, thought it was a little funky. So let's get ourselves started. One other just quick thing to tell you. WebAssign for me works a little bit funkier than it does for all of you, or than it does than probably Wiley did before. Wiley before I could put a penalty if you did it after the due date, and it just automatically put it on. In order for me to put the penalty on, I actually have to go in and manually do that. So after each one is due, I will go in and manually reopen them. If you get to a point you're trying to do something after the due date and you go in and it won't let you, just let me know and I'll go in and make sure that penalty. The neat part is I only have to put that penalty on for those of you that don't have full credit. So if you already have full credit on it, doesn't matter. So I just go in and I manually put in on the 2 or 3 people that don't yet have full credit, and you can keep working on the problems. So couple of quick things. Again, exam on Wednesday, review sheets are posted. Ends with continuity. The review sheet's a good indication of what's on it from the material that that's from the beginning of chapter 1. Just a couple quick things that I didn't point out that are in your notes. This is the continuity section. And so here's our continuity section. There's a chart in the continuity section. I just want you to realize or to see. It actually it gives a whole bunch of functions, gives their graphs. It talks a little bit about whether the function has a value at 0 and whether the function is continuous at 0. And so it hits all the different options of things that we talked about. So, it starts with f at x equals x. So that's the line y equals x. F at 0 is 0. It's continuous. There's no holes, jumps, or gaps. And that's yes?
You get a card for the exam, right?
Yes, you get a card for the exam. 3x5 card, one side, anything on it your heart desires. Yeah, the rules are still the same this semester. Good question. I forgot to mention that, but yes. It'll be exactly the same rules as we had before. Second function, x squared over x. Now notice if you simplify that, that gives you y equals x, but that's the one where we talked about last time. It actually has a hole at the origin because we try to substitute in 0. There's a fancy name. Remember I used the term discontinuity the last time? There's a fancy name you'll sometimes hear people talk about with a function like that second one. This right here so we know where we are. That's actually the kind of discontinuity they have there is what's called a removable discontinuity. And it's sort of intuitive what we mean by that. By moving one dot or putting in one point, we can actually remove the discontinuity. So that is a special name. It's called a removable discontinuity. Whereas when I look at the next one, 1 over x, right, it actually is discontinuous, does not have continuity at x equals 0. Right? There's no value when x is 0. That one does not have a removable discontinuity because there's not a single point I could put in that would actually make it a smooth, unbroken curve. When I did x over x, which if we simplify it looks like y equals 1. But remember again, because the 0 would be a problem in the original, that we have that hole in the graph. Again, removable discontinuity if I use the phrase. Couple more, and some of these we're going to see again. I did the absolute value of x, sine x over x. This will revisit us. That one doesn't write. This right here is one we'll revisit. We'll talk about later on in the course. It's one of the more famous ones. It actually, again, has that removable discontinuity. It's not defined at x equals 0. Then I get absolute value of x over x, 1 minus cosine x over x. Again, that one has a removable discontinuity. And then the one that's the funkiest of the whole group is sine of 1 over x. If you actually graph that, it does what sometimes textbooks will refer to as it oscillates wildly. That's kind of the fancy phrase that you'll sometimes see it referred to, that it oscillates wildly. There's actually a hole right there at 0, 0, but it also just does this wild up and down thing. So there's several things that are going on there. There's a hole and it has this wild oscillation. So I wanted to point that page out, and I wanted to just quickly point out the last page of that section. And I want to just point out something that's called the intermediate value theorem. This is one of those, and you'll see several of them in this course. This is one of those, I'll call it duh. Yeah, that makes sense. It's sort of obvious, and somebody gave it a name. Okay, so what the intermediate value theorem says, I'm going to draw a new picture of it, says if you know a value of a function, say at this point, and you know the value of the function at this point, and I know the function is continuous between those 2 points, so there's no breaks, that I can draw a complete curve without lifting my pencil in between those 2 points. And it could be a straight line, it could be some curve, it could wiggle around, it could do, all kinds of things. If I have a continuous curve or line or what have you between the 2 points, then what I know is this function has to take on every value of y in between this value and this value. So this had to happen to have a y equals 1, and this happened to have a y equals 11. That someplace in between we have to pass through y equals 7, and y equals 8, and y equals, 2.3, and y, that it basically the intermediate value theorem says if you're continuous, you have to pass through every y value from the start to the end. Probably not terribly earth-shattering. You might pass through other y values. I mean, we could actually have so you go through even higher values, but really all the intermediate value theorem says is if this is, say, y is 1 and this is y is 5, it tells us that we have to go through every y value between 1 and 5. And that we could actually find the x or x's that do that if we wanted to. Again, not an earth-shattering theorem. So that's what if you happen to read that, that's what that kind of gobbledygook math-ese kind of sounds like. So again, that's the end of the material that we see on the exam. So then we can move in and start talking about 2.5. I am not asking you about any limits that that go to infinity. We saw a little bit of the limit as h goes to 0, and we did the algebraic, or x goes to 0, or we did end up with limits that gave us infinite values. What the difference is here, the part that I'm not on the exam, are things where you have either the limit as x goes to infinity or the limit as x goes to negative infinity. So that's what I didn't put on the exam. We still may end up having limits where the answer is infinity, but this particular subset we will not put on the exam. Not that hard, but I just didn't want to talk about it one day and test on it the next. So first of all, the beginning we've already actually done. The limit as x goes to 0, something like 1 over x squared. We could argue that it doesn't exist, or, and this depends on what the textbook is. You know, some textbooks say it doesn't exist because they define limits as finite numbers. Some textbooks and some people will say the limit is infinity because both tails go to infinity. So I try when I do these to be very specific. I will say, if the limit goes to infinity, please say so. And I think that you saw that on the WebAssign a fair amount as well. They'd say if the limit's infinity, put plus infinity, or put plus infinity, or minus infinity, or plus inf, minus inf types of things. So I try to be specific to get that information from you. And so in this case, I would generally say the limit's infinity. But again, some books will say doesn't exist. And so there's a whole definition that goes with that. Whereas, and this one actually does some other stuff, whereas though if I looked at this particular, and I'm really focusing on when x is 3, the actual limit here does not exist. If I just say the limit as x approaches 3, that doesn't exist because the limit from the left goes to negative infinity, the limit from the right goes to positive infinity, and since they go to two different places, that clearly does not exist. And so your textbook and I talk about the fact we would then just look at the limit from the left or the limit from the right. So your book does several different examples. And again, that's pretty much the material we talked about that I said, you know, that might end up on the exam. So here's the part that won't. Limits at infinity. So in this particular case, what actually is going to happen is we are going to be looking at the limit as x approaches infinity. And it's kind of funny because they will use the language, the limits at infinity. Now, it kind of makes me chuckle because you never really can get to infinity, but that is kind of a math phrase that they use, is this limit at infinity. So typically, and it's not always the case, but typically a big set of ones we look at are functions that are rational functions, fractions. They're going to be fractional functions. And so if I look at fractional or rational functions, there's three situations that can occur. And I'm hoping these three situations kind of ring a bell from something from pre-calc. Okay. One situation is if the degree of the numerator is less than the degree of the denominator. And when that's the case, we say the limit's 0. And these are talking about rational, or when situations where we have polynomial numerators and polynomial denominators. So put an example up here. Now, if I wanted to, if you're like, okay, Do I have to remember that? Well, you probably don't. It'll make your life a little easier. But notice I can actually do this by throwing this gem in my calculator. So that's what I'm doing here is I'm just typing away. Divided by 2x raised to the third minus 1. So there's the function. Remember, I put the numerator in parentheses. I put the denominator in parentheses. And I'm going to make sure I have what I call an ask table. So I'll make sure my independent variables on ask. And now I'm going to do a table and clear out what I have. If I want to do the limit as x approaches infinity, what kind of numbers do I have to pick? What'd you say?
Positive numbers.
Positive numbers, yep. What'd you say after that?
Large ones.
Large ones, large positive numbers. So let's start with not so large positive numbers. Suppose I start with 1. I get, then maybe I could go to 10. And then maybe I go to 100. And notice by the time I get to 100, maybe I'll do something, go to 20. There we go, that helps a little bit. So notice when I get to 20, I'm still dropping. I went from 13 down to 0.056, down to 0.013. Maybe I'll go to 30. Sometimes if I go too fast, it's harder to see. And notice 0.00. And if I go to 40, I'm dropping down. And 50, dropping down. And 60. And for me, sometimes it's hard to tell. Am I going down to 0.001? Maybe I'm doing that. So I need to find out, okay, well, it's still 0.001. 80. Oh, now I notice, if I move this over, that if I take a look at that, that's now 0.000. And so now I'm starting to be convinced that it's going to 0. I will warn you, and I don't know if I can make it happen on this one. On some of the problems, if you use too big a number, you can make the calculator cough up and give you error messages and bizarre numbers. I guess this one I wouldn't get that. Notice, look at that, when I pick 1 with however many zeros, that I'm at 6 times 10 to the negative 20th. So I'm pretty well convinced this is going to 0. Of course, I can also try to convince myself by looking at the graph. And notice as x approaches infinity, that would be going off to the right, it does also look like it's going to 0. So the graph kind of confirms that. Or I can say, hey, in this case, the degree of the top is smaller than the degree of the bottom. Said another way, both the top and the bottom grow. Both of those get huge by themselves. But the top gets huge slower than the bottom does. So the bottom is going to overpower the top. Case 2, whoops, if the degree of the numerator is the same as the degree of the denominator, then the limit as x goes to plus or minus infinity is going to be a over b, where a is the leading coefficient of the top and b is the leading coefficient of the bottom. Does this sound at all familiar? Did we talk about this, except maybe without the term limit last semester? You bet we did. There's an algebraic technique, and I'll actually show you on this one, the algebraic technique. Your textbook talks about this. This is actually kind of the shortcut way. What your textbook would actually have you do, many textbooks will, is they would actually have you take a look at the numerator, take a look at the denominator. And this is true for any of the problems. Take a look at the numerator, take a look at the denominator. And what we want to do is basically divide the numerator by the highest power of x that appears any place. And then we do the same thing in the denominator. And so in this case, we would divide the numerator and the denominator both by x squared, because that's the highest power of x that appears any place. And if I do that, when I do that division, that's going to give me 5 plus 8 over x minus 3 over x squared. And then this is going to give me 3 plus 2 over x squared. And now I can let the limit go to infinity again. And based upon what we already said, we know this goes to 0, this goes to 0, and this goes to 0. And so the limit becomes the 5/3 that we can do just by using the leading coefficient. That's the algebraic technique. If somebody says, oh, do an algebraic technique, you're really going to divide by the highest power of x. That would actually work up here. Let me show you up here if I did that. Here I'd look and my highest power of x is x cubed. So divide top by x cubed, bottom by x cubed. And if I did that, keep my limit notation, try to be good. If I do that, this is going to give me 11 over x squared plus 2 over x cubed over 2 minus 1 over x cubed. And now what you'll notice is the top goes to 0 and the bottom goes to 2, and so the whole thing's going to 0 over 2 or 0. So if you can't remember the 3 rules, you could actually run that. Divide by the highest power of x. And then the third case is if the degree of the top is larger, if there's more power in the numerator. Then what's going to happen is we're either not going to have a limit, or we're going to have a limit that's infinity or negative infinity, and we then just have to figure out which one it is. And so I did an example out of that as well. So that's really, quite honestly, all there is to limits at infinity. And if I'd had kind of a few more minutes of time, if we'd been, I could have thrown those on the exam, but we'll not approach those, you know. The mean math teacher could, you know, sneak that on as some sort of a bonus question or something to see how much you remember from today, but that would be about the extent. It will not be a regular exam question. So that lets us move into the calculus of the class. And as I said when we started the class, that we're doing this thing called derivatives. We spend a lot of time doing it out longhand. Then we get some shortcut rules. Here we are. We're now going to formally, for the first time, use the term derivative in section 2.6, and we're going to be working on doing the derivatives longhand. The cool part is you've done all the work. We've actually done this. It's just now putting the terminology with it. So, just some terminology piece. I actually want to take a look at the student learning piece that's going to be coming into these notes. So by the time we're done with the section, you should be able to, in fact, coming into this course, you should be able to set up the difference quotient. That, by the way, if you say, what do you mean by the difference quotient? F at x plus h minus f at x over h, or f at 1 plus h minus f at 1 over h. That expression right there is what's called the difference quotient. If I throw the limit in front of it, limit is h goes to 0, f at x plus h minus f at x all over h. That's what we call the limit definition of the derivative. Please do me a favor. Never ask me what I mean by the limit definition of the derivative. Because I'll probably answer and say, I think we should know what that is by now. Because once we have it here, we need to make that connection and know what that is. Now, I'll say it, and somebody will ask, and then you will all I'll hear this like chuckle that happens in the background. So we'll see if somebody asks, what do you mean by the limit definition of the derivative? You know, you can all give that uncomfortable chuckle. Sound like a plan? Are you awake? Yeah. How are we at Copenhagen today? Good? You guys become like the most popular news community since Channel 7 hired Asa. Did you notice that? Yeah. And they're always, if they need a story about the school, they're at your school. Yep. That's called having connections. Oh, I forgot to tell you, I saw Mr. Staub on Saturday too. He was at, I was just leaving Dunkin' Donuts, and he and his family were just going into Dunkin' Donuts on Arsenal Street. I didn't ask him where he was going. Could have been going lots of places, but it was about 20 minutes before the start of Super Science Saturday, so he might have been going there even, or something else in town, but he had the kids with him. I almost walked right into him. I was too busy trying to make sure I held the door open for the little guys. So, and quite frankly, usually I can walk right past people and I don't even recognize them. I'm in my own world when I'm out and about town. So then what we're going to do is find the derivative of a function at a given point, algebraically and numerically. Quite frankly, that's the algebra for part A, or letter A. And then comprehend that the derivative at a point is a number. Then we're going to be talking about it, that if we have a physical point, the derivative is a number. And of course, we said that number is the slope, right? And recognize that derivative then is the slope of the tangent line. We're going to want to make sure that we can find the units, and we already talked about that a little bit. The neat part is it's change in y. It's equivalent to the idea of change in y over change in x, so it's the y units over the x units. Interpret the numerical meaning. And then this notation. And I'm actually going to start right with that, even though it's kind of the last thing that's written. Instead of writing out every single time on a problem, find the derivative. I don't know about you, but I'm kind of lazy. Find the derivative. Do you want to write that out every single time? Do you want to write out the derivative is in words every single time? Probably not. So there's two notations that we use when we talk about the derivative. One looks like F with a little apostrophe. That is read either the derivative of F, or if people want to be real shorthand, you'll hear a lot of people refer to as F prime. Means the first derivative, the derivative of the function. And another notation that we'll see looks like dy over dx. Means the derivative of y with respect to x. And hopefully when you look at that, you look at it and you go, wait a minute, that looks a little bit like delta y over delta x back from algebra class. It is. It's meant to actually make you think of that. Those two notations, the f prime and the dy over dx, those two notations are interchangeable. You might go, well, why do we have two definitions? Well, I'll give you a little history lesson, a little tiny history lesson. Back in the late 1500s, early to mid 1600s, was when this concept of the derivative was coming forward, was really being kind of talked about. And there were two mathematicians at the time that were really kind of the leaders of talking about it, and in particular talking about it more publicly, more likely that kind of publishing their work. One of them is one that's going to be very, very familiar to you, Sir Isaac Newton. Okay? Newton, when he was doing this, he had a notation, and it was actually called Newton's dot notation. And what he was doing was he was putting a dot over the top of things. That dot is what became the apostrophe. And so that apostrophe is largely coming out of Newton and Newton's work. The dy dx was another mathematician. It's actually a German mathematician, and depending upon your German, you either call him Leibniz or Leibniz. He was working at almost exactly the same time, and he was working with the concept of slope. And he wanted some notation that would differentiate it, no bad pun in turn, and kind of meant, but they would tell it separately from the concept of change in y over change in x. And he started talking really in terms of that relationship, and that dy over dx notation came from him. And so two different mathematicians, two different notations, they've merged, and we use them interchangeably at this point in time. There's a long standing debate, and it depends whether you believe in the kind of Newton calculus or the Leibniz calculus as to who actually discovered, quote unquote, the concept of the derivative. They were really talking about it a long time before then, but they were really the first ones to publish it. Really kind of an interesting little story. It was actually a Jeopardy clue a month or two ago. Leibniz was actually the answer. I was like, ooh, I know this. My husband looked over at me. There goes the geek again. You know, I've been so excited. I don't know, you're probably not all Jeopardy watchers, but I've been watching Jeopardy, and it's a teachers tournament, and like every second or third night there's a math category. I'm like, ooh, life is good. Oh well. Back to the notes. So this kind of rehashes, really says a lot of things that we just said. It says this ratio is the difference quotient. Right? And if we wanted to find the average rate of change or the difference quotient, I'm going to put that phrase here too. At the point where x is 2, we're really going to be using this f at x plus h minus f at x over h, or f at a plus h minus f at a over h. And we'll substitute in the 2, and we do the algebra. This algebra is, like, remember, super important. Now this one I picked on purpose to take a look at because of the cube that's in it. And we'll come back to the cube. Then once we have this set up, we can do the instantaneous rate of change. And again, instantaneous rate of change, interchangeable with the phrase derivative. The only difference between what we did before and what we do now is we're looking at the limit as h goes to 0. And notice, there's that derivative notation. This would actually mean the derivative of the function at the value where x is a. So I actually did that here. And I want to kind of show you this example because we can do this numerically or we can do it algebraically. You have to be a little bit sensitive to the fact that the math teacher sometimes may ask for numerically, often will ask for algebraically. There are some problems that we'll do later on when we do all the shortcut rules that you actually cannot do algebraically. If I wanted the derivative out longhand of e to the x, there isn't any algebra I can do. Exponential functions are problematic. Logarithmic functions are problematic. Trigonometric functions are problematic. So the ones we typically do algebraically are going to be polynomials and rational functions, things that involve x squared and x cubed and things like that. So there's my 4x cubed at x equals 2. So I did f at 2 plus h minus f at 2 over h. So there's my, put the 2 plus h in place of x, put the 2 in place of x. And then I actually just put this puppy in my calculator. I'm going to give you some advice. Try to get those numbers. Make sure that you're comfortable with doing that on the calculator. Because sometimes students say, oh yeah, I know, I can put that in the calculator. And then they get to something where they have to do it on an exam or a homework assignment and it's not working for them. So on the ones where the work is done out, convince yourself that the numbers are okay. And so then notice the numbers I picked. I picked numbers from both sides that go into 0. So notice on the positive side I picked 0.1, 0.01, 0.001. Now, I convinced myself, you might not be convinced. And if I were doing this, I probably wouldn't be 100% convinced either. But I convinced myself that it must be 48. But notice, I really only made it down to 48.024. I would probably still do 0.0001 and 0.000001 just to see it go a little bit closer, just because I can. And then typically I wouldn't do, once I was convinced on one side, I wouldn't do more than 2 or 3 values on the other side. And so it looks like this is going to 48. And so notice the notation. This is telling me f prime at 2 is 48. So the derivative at 2 is 48. Or in other words, if I graphed 4x cubed, so let me do that, 4x raised to the third. So if I graph that, and if I happen to look at where x is 2, and so let me just for fun go from 0 to 5 on my x's, and play with the y's a little bit here too. Let's make my min be -1. Now if I went to where x is 2, let's do this. Shows it up a little bit. If I went to where x is 2, and I drew the tangent line, however that might be, the slope of that line would be 48. Anybody want a way to cheat? Math teacher's going to make you do all the work, but I can show you how to cheat. No answer, so maybe you don't want to know how to cheat.
Make us do all the work, why would we want to know how to cheat?
You can check your answer. Would you like a quick way to check your answer? Yeah, maybe.
Why not?
Why not? So, remember the old calc menu? Remember that second trace? And if we go down through, right, in the past of your back algebra, you did item 1 and 2 and 3 and 4 and 5. Oh, look at item 6. Look what it says. Did you ever notice that dy over dx before? Nope, you probably didn't. Or you might have said, I wonder what that is. So if I pick item 6, and then I type in the number. So the number I was worried about was x equals what? Do you remember? 2. So if I type in 2, dy over dx is 48.000004. Now you have to be a little careful because the calculator is using a numerical algorithm. And so it'll often give you a number that's just a tad bit high, or it might give you 47.999997 or something. And you have to realize that you'd probably round to the closest thing. Isn't that pretty cool? Okay. Yes. Now, I'm going to go one step further on this before I do the other piece. And suppose I asked an additional question. Suppose I asked a part B, and then we'll do the algebra. Suppose I said, let's write the equation of the tangent line to f at x equals 4x cubed at x equals 2. That 48 I just found, what is that?
Slope.
That's the slope. So I now know the slope is 48, and if I want to write the equation of a line, I need the slope and I need the point. Yeah, so what I know, based upon what the question is, I know that the x value of the point is 2. And so I just need the y value, which, by the way, if you look at the work that I did there on the other part, is actually 32. 2 cubed is 8 times 4 is 32. Now I take the slope, I take the point, and I do good old pre-calc. So y equals 48x plus b. 32 is 48 times 2 plus b. 32 is 96 plus b, so b is going to be negative 64. My math is correct. We'll check to see in a minute. Do you want a way to check that answer as well? Oh, yeah. You got this really cool, this is like something that is one of the first times that I ever use this when I teach here. Under, if you look at the calculator, there's this draw menu. Usually when I give the calculator to an 8-year-old and you show them the draw menu, they're using it like an Etch-a-Sketch. Well, actually, under the draw menu, you'll notice that item 5 says tangent. Right? You see item 5 says tangent? I can pick item 5, and again, I picked the x value, so x is 2, so all I did was press the number 2, and it went to that x equals 2. And it draws the tangent line, and it gives me the equation. Again, I have to deal with the round-off piece. Ooh. Ah, fireworks. So, cool way to be able to check if you have one of these problems. So it's under the draw menu. Then, by the way, if you wanted to do a different problem, you could either, if I want to do the same thing, and I wanted a different line, suppose I wanted it x equals 1, press the enter key. It'll just keep drawing the lines, and so until if you're working with the one function, it'll kind of keep that stuff. So just realize that if you want to get rid of it, you either do a new function, or option 1 is clear the drawing. And so it'll just go back to the regular graph. So under calc, you can get the slope, and under draw, you can draw the line. I'm the only one who's excited about that, but that's okay. You're just quietly excited. Then we can actually do this out algebraically, and this one I'd like to talk about a little bit here, because notice to do the derivative algebraically, I have to cube 2 plus h. This is why sometimes students are like, oh, get to the shortcut rules, will ya? Because you got to cube 2 plus h, which means we have to go 2 plus h times 2 plus h times 2 plus h. Right? And so we do the first 2, and then multiply that again by distributing another 2 plus h, and you end up getting this. There's other ways of getting that, but for right now, we'll just work with the algebra. And so there it goes in there, multiplied by the 4. And then notice the 32's cancel. Take out an h, because I didn't do that step in here. 48 plus 24h plus 4h squared all over h. H is canceled, we get the next line, and then we can do direct substitution, make h be really, really, really close to 0, and that's going to give us 48. You should be really good at that. You need to make sure you're really good at that. This right here, this section in terms of the theory of calculus, this is the most important section of the course. In terms of the theory, this is the most important section.
So to get your y value of the point, you just plug it into the original function?
You plug back into the original function, yeah. Yep, good question. So then what I did was I did another one that's kind of that same level at a equals 1 or at x equals 1. Whoops, can't see. A equals 1. Sometimes you'll see the book use a equals 1. Sometimes they'll say x equals 1. They'll use the notation interchangeably. So here's our limit definition of the derivative. So again, limit definition of the derivative. Sometimes you see the word limit in there. Sometimes you just see definition of the derivative. So f at 1 plus h, remember, I'm just going to do this out. To do f at 1 plus h, you put the 1 plus h in for each of the x's. So you have 2, 1 plus h squared plus 3 times 1 plus h. Make sure you can do that. Make sure you can do it well. And then, of course, f at 1 is the easy part. 2 times 1 squared plus 3 times 1. In that case, that's 5. When I put all of that in and I did all the steps out here, you'll notice, by the way, I followed my own rules. I wrote limit at every single step. Again, we could use the arrow if you're writing down the page. So if I simplified this whole mess, that whole mess simplifies into that. The 5's cancel. Factor out an h. The h's cancel. And then I'm just left with 7 plus 2h. When h becomes 0, I get 7. So I can say f prime at 1 is equal to 7, or I can say the slope at x equals 1 is 7. I can say the instantaneous rate of change at x equals 1 is 7. All of those are saying exactly the same thing, just in different phrasing. What do you think? With practice, think we can do this stuff? Yeah, just need to practice. Notice I did 2 others. I did this one with the fraction. Find the derivative at x equals 3 algebraically if f at x is 1 over x plus 2. This one's tricky, has fractions. You don't like fractions. Make sure you practice it. So if I want to do it at x equals 3, this right here is kind of the setup. So we do f at 3 plus h minus f at 3 all over h. And then remember to do f at 3 plus h. We put the 3 plus h in for the x. So there, instead of the x, is the 3 plus h. So it gives us 1 over 3 plus h plus 2. And then I do f at 3. And so I put the 3 in for the x. And then when I simplify, I get 1 over 5 plus h minus 1 over 5 all over h. Looks kind of like a limit we did last time, doesn't it? Now, I didn't do this the way Ryan told us to do it the last time. I did it the way I said, oh, we can save ourselves some work. And so what I did was I looked at this and I made everybody a fraction. So this h, I'll throw over 1 because it's not a fraction. And I found the least common denominator. And so the least common denominator is 5 multiplied by 5 plus h, or 5 plus h multiplied by 5. And then what I did was I multiplied the entire fraction by the number 1. It's just my number 1 is 5 plus h times 5 over 5 plus h times 5. Notice when I do these, and every time it's a derivative question, this will be true. Notice when you do a derivative question and you multiply by this, the denominator, you just paste those pieces together. Do not multiply them out. So, don't multiply those out on the bottom. Make that clear. On the top, I distribute this through. So I take the 5 plus h times 5 times each of the fractions. In the case of the first one, the 5 plus h's cancel and leave me only with the 5. And in the second case, the 5's cancel and they leave me only with the 5 plus h. Notice, by the way, the minus sign. That material that follows it after I do the cancellation must be in parentheses because I get sign changes. That negative has to distribute. When I do a little simplifying, I end up with a negative h on the top and h in the bottom. They cancel. Gives me negative 1 in the top. This is kind of cool. I have a hole right where the answer is. So why don't you tell me what the limit is? I know what it is, so why don't you tell me what it is? How do I do the limit? What do I do at this stage? I heard some bit of mumbling. What did you say? Put 0 in for h. When I plug 0 in for h, the top is still negative 1, isn't it? And if I plug 0 in for h, 5 plus 0 times 5, so in the denominator I get 25. Yep, so I get minus 1 over 25.
Oh, will that always be square root of the first fraction?
Depends on the problem. We will learn that if you have something of the form 1 over x plus a, we will actually learn that the derivative is always negative 1 over x plus a squared. And so, in this case, x was 3, and x was 3, and the a was 2, and so you get that negative 1 over 25. That is that pattern. If this is your problem, and I'm taking the derivative, that is what the derivative will always be. I'm not recommending that you memorize that, because you'll notice I had to think for a second because I actually run the rules. Remember I mentioned that sometimes we can't do them algebraically. This is one of them where we can't do them algebraically. So I want to do a numeric question. Find the derivative of f at x is 5 to the x at x equals 0 numerically. And so notice this time I used find the derivative. I'm starting to use that language. So setup is f at 0 plus h minus f at 0 over h. Substitute that in for the x's. So I have 5 at 0 plus h minus 5 to the 0 all over h. When I simplify, that gives me 5 to the h minus 1 over h. There is no algebra I can do. And so this one I actually have to do out numerically. And this is one of those where the limit doesn't go to a pretty number. And so you have to kind of guess. And I just want to talk about this just for 10 seconds here. You have to kind of guess. I did 0.1, 0.01, 0.001, 0.0001. And what I start to look for, and this is the phrasing I use, are kind of frozen decimal places. So I notice all the way through, I start with 1 plus. So I know my answer has to be 1 plus. Then I notice as I keep going, the 6 seems to freeze. So it's 1.6. Then as I keep going, I notice that it looks like it's becoming a 0. And so I'm at 1.06 or 1.60, then it looks like the 9. And so I can start to look at this. And if I went far enough, I would actually find that the 4 will eventually freeze. It will end up being 1 point, and it keeps going. It's an ugly decimal. So I have to look for kind of those frozen decimal places. That's the way that you can tell. Then I wrote an equation of a tangent line. So what do you think? Good place to quit? Yep. What are we doing for Wednesday? Yep, collected homework. There's an exam. I'll have a little handout with some other information on Wednesday as well that I'll stick on here. But exam on Wednesday. Have a great day. See y'all on Wednesday. Back to the board. Stop. I have to wait for it to stop blinking again. Now, do you have to go all the way across the
Building.
rules? Yeah.
There, last semester, my class was right here in building 3.
Yeah, because it couldn't happen that way this semester, but